So Chapter 6, Section 4, we're going to be focusing on some applications. And so the application that we're going to be focusing on in this section is work. We're going to see a couple of other ones. But work, in physics, force is defined as mass times acceleration, or as we may have seen Newton's second law, F equals ma. This is Newton's second law of motion. We know that if the acceleration is the second derivative of position, because when we take derivatives, if we have a position function, the first derivative is velocity, and the second derivative is acceleration. So rewriting using our calculus notation, we get F is equal to m times d2s dt squared, where s is the position function. And SI, or MKS, in the Mks system, which is the metric system, the units of force are called newtons, named after Sir Isaac Newton. And the units of force are kilogram meters per second squared. So if a force of 1 newton acts on an object with a mass of 1 kilogram, we get meters. So if a force, that's not written down correctly, a force of 1 newton acts on an object with a mass of 1 kilogram, we get meters per second squared, but then we have kilograms times kilograms, so we get kilograms. So meters times kilograms squared per second. So the acceleration of the object would be 1 meter per second squared. So actually I have this. So if a force of 1 newton acts on an object with a mass of 1 kilogram, we should get our acceleration there. So the acceleration would be 1 meter per second squared. So my problem with this is, so force is a newton meter, and newtons are sorry, I've got that equation set up backwards, is the problem in the notes. So let's cross this thing out for a second and update this. So let's actually fill this in. So we know force is equal to mass times acceleration, and we know that our force is measured in newtons. So if our newtons are kilograms meters per second squared, so our newtons right here, we have kilograms times meters over second squared is equal to mass times acceleration. To solve for the acceleration, we would divide by m and divide by m. So those cross out, and then our m's would cross out. Sorry, now I'm doing that backwards. I'm killing myself today. My glasses are giving me issues. So let's do this the proper. Let's back up just a little bit. Oh, I see what's happening. All right, I'm causing all sorts of problems. So let's get rid of this. So we have force equals mass times acceleration, but I need to write down the units for each of these. So we have kilograms times meters over second squared. Mass is measured in kilograms, so just to be clear, what was happening is I'm using m in too many places. So this m is this m, this m is this m, and then we have our kilograms from here, and our seconds from here. So this equals mass times our acceleration, which I'll just denote in red. And that's what we're solving for. So when we divide by kilograms, and we divide by kilograms, our kilograms reduce out, giving us the acceleration, which is what it should be, meters over second squared. So that would tell us that if we had 1 Newton, it would cause an object with a mass of 1 kilogram to accelerate at 1 meter per second squared. We define work to be force times distance. So the units of that would be, if we have our newtons or kilograms meters per second squared, if we multiply that again by a distance, so meters, we would get kilograms meters squared over second squared. And the units of work in the SI system are called joules. So the unit analysis can be helpful, as we'll see in some of the problems that we're going to do shortly. So let's take a look at our first example, which will involve pure algebra and no calculus. So how much work is done by lifting a 7.5 kilogram bowling ball 75 centimeters above the ground? So there's a couple of things we need to be careful with in this. So the first one is that we are using the Mks system, and Mks stands for meters, kilometers, and seconds. So whenever we're doing physics in this section, we need to make sure that all of our measurements are in meters, kilometers, or seconds. If they are not given in one of those 3 things, we are going to have to convert from that to something else. So we're doing good so far. Our mass is 7.5 kilograms. So that one's okay. But then we want to know, well, how much work is done by lifting 7.5 kilogram bowling ball 75 centimeters above the ground? Well, there we do have a problem. So our distance is 75 centimeters, but we don't want centimeters, we need just plain meters. So how do we convert something from centimeters to meters? So there are a bunch of different ways to do that. The way I prefer is I'll make a unit fraction, and we need to know the conversion. So 100 centimeters is equal to 1 meter. So we're going to create a unit fraction by dividing both sides of that by something. We want to cancel out centimeters, so our unit fraction would be, we're going to divide both sides by 100 centimeters. So that tells us then that 1 meter over 100 centimeters is equal to 1. So 1 meter over 100 centimeters. And then our units would reduce out, and we would have 75 over 100, which would reduce to 0.75 meters. So there's a bunch of different ways to do that. I prefer the unit fraction method because especially when you're doing more complex dimensional analysis, it's a lot easier to set them up this way. So now we have our mass and we have our distance. So now we know that force is equal to mass times acceleration. And we know work is equal to force times distance. So we're going to have to calculate some of these things. So we've been given a mass, so we know this. And we've been given a distance, which is this. So in order to answer the question wants work, we need to know the force. But in order to find the force, we need to know the acceleration of this object. So when we're lifting a bowling ball on planet Earth, unless there's some external force, the only thing that's acting on it is the acceleration due to gravity, pulling everything towards the center of the Earth. So in the Mks system, gravity and for gravity we use the symbol lowercase g. We have that little g is equal to 9.8 meters over second squared. So in our homeworks or in any of our applied problems in this section, if we need the acceleration due to gravity in the Mks system, this is the one, 9.8 meters per second squared is gravity. So the first thing we need to calculate is our force. So our force is going to be equal to our mass, which is 7.5 kilograms, times our acceleration, which we now know as being 9.8 meters over seconds squared. So we multiply these things together, so 7.5 times 9.8, and we get 73.5 for our force. So our force is 73.5, and then our units are kilograms times meters all over second squared. And indeed, kilograms times meters over second squared was our definition of a Newton, a kilogram meter per second squared. So now we have our force. To calculate our work is equal to force times distance. So we have our force is 73.5 kilograms times meters over second squared times our distance, and our distance we calculated above as 0.75 meters. So now we take that and we multiply by 0.75 and we get 51.125 kilograms, and then we have meters times meters, so that's meters squared all over second squared. And if we check our units for that, we notice that kilograms meters squared per second squared are our joules. So the work is 55.125 kilograms, kilograms meters squared per second squared, or joules. So one thing that is worth noting, and it will be helpful in the U-try you're about to do, in the MKS or the metric system, the unit of force is a Newton. Well, it turns out in the English or the imperial system, the one that we use in the United States, we have the most common unit is actually a unit of force. So in the imperial system, the pound is the unit of force. So we don't need to know this, it's just a fun bonus fact. But in the imperial system, mass is measured in slugs. Nobody uses those, but if you find some old school engineering books and stuff like that, you'll find things that have masses in slugs when you need them. So the imperial system uses force, so pounds are actually mass times acceleration and not just a mass. So keep that in mind. There's going to be a little bit different when we set up these types of problems. So remember, what is work by definition? Force times distance. So if you're given a force in pounds, or if you're given pounds, you know it's a force. Unlike in the Mks system, you're not going to have to calculate a force because you're not given a mass, you're given a force. So keep those two things in mind, that they are slightly different. All right, so we want to calculate work, and we know work is equal to force times distance. Well, we were given 11 pounds, and 11 pounds is a force. So our force is going to be 11 pounds, and then our distance is 2 feet. So we're really going to get 11 times 2, which is going to give us 22, and then our units are going to be foot-pounds, which is the unit of work in the imperial or English system. So one thing about that, calculating work is a lot easier in the imperial system because you're dealing with forces as opposed to masses. All right. So now the question is, we've been doing things that have involved absolutely no calculus, right? That was just multiplication of some different things. So now we want to generalize that idea and start to see the true power of calculus. So we hinted at this in the previous couple of sections. We found volumes of things, and how did we do that? We imagined cutting them up into little tiny sheets, finding the volume of each of those things, and then adding them up, treating each of the bits in that formula as if they were constant on those teeny tiny little dx strips. Well, we're going to do something similar here. So what happens if the force is not constant? Well, if we subdivide the domain of the force function into small delta x intervals, on each subinterval, we have the amount of work that is done is equal to the force at that point times delta x. So, sorry, there shouldn't have been a delta on the f. So taking the width, actually there should have been. I'm thinking of something else. So that's fine. Taking the limit as the width of each interval goes to 0. So imagine our force is changing. So let's pretend for a second, we'll justify this with a picture, that you're pushing some block, but as you're pushing, you start pushing harder and then eventually you stop pushing less. So force is equal, or work is equal to force times distance. But if our force is changing at every point and how far we're moving is changing at every point, our delta x, we could have a whole bunch of little forces and have them act on that object, giving us the change in work at each of those points. So kind of like when we were cutting things up into strips, if we add up all of those teeny tiny delta W rectangles, it will tell us the sum of all of those will give us the total amount of work done. So the way we do that is we're evaluating the same type of Riemann sum. So the total amount of work would be the integral over the entire distance from A to B of our force function dx, where the force is changing at each point. So the big idea, and we're going to see this a lot in the applications we're going to do, is calculus lets us treat things like they're constant. Because imagine if you zoom in far enough, everything looks like a straight line, right? And that's the power of calculus. So if we take a teeny tiny chunk, we can treat everything like it was up here, where we were using constant forces and constant distances. And then, since it's really changing, the way we take the change into account is to integrate over all of those tiny changes and add them up. So the integral is really the workhorse of physics and a lot of other things. So as the story goes, you know, they talk about Sir Isaac Newton inventing calculus. He was actually trying to solve physics problems. And so calculus was a necessary tool for him to do that. He wasn't doing it for math's sake. He wanted to deal with problems like this, where we have forces on planets and other things that are changing, and he wants to solve those problems. So it gives us a very nice strategy to do so. So let's take a look at our first example. And I cut off the hint ninja, but we're going to want to listen to him because the hint ninja is wise. Always listen to the hint ninja. So the first thing we want to talk about is Hooke's law, which is a physical observation law from physics. So the force required to stretch a spring x units beyond its natural length is proportional to x. That is, F is equal to kx for some k, where k is the spring constant. The thing that we probably haven't done for a while that we want to take note of is directly proportional. So this is actually just an equation for direct proportionality, right? The force is directly proportional to the distance. So in our problem it says a force of 3 newtons is required to stretch a spring from its natural length of 10 centimeters to 15 centimeters. How much work is done stretching the spring from 20 to 40 centimeters? So first thing we need to do is notice what were our units of distance given in? Centimeters. What do they need to be given in? Meters. So let's do some conversions. 10 centimeters is 0.1 meters. 15 centimeters is 0.15 meters. 20 centimeters is 0.2 meters. And 40 centimeters is 0.4 meters. So now that we have that out of the way, we need to figure out, well, how far was our spring stretched so we can calculate our proportionality constant that we have up here. So it says a force of 3 newtons is required to stretch a spring from its natural length of 10 centimeters to 15 centimeters. So one thing, if you think about a spring, it's never 0 centimeters long, right? Because that wouldn't even make any sense. So when it's at rest, the spring is neither extended nor contracted, right? Because if you push a spring in, what's going to happen when you let go? It pushes back out. And if you pull a spring out, what's going to happen? It's going to pull back in. So springs work in both directions. So at rest, we know the length of this is 10 centimeters, and then we stretch it to 15 centimeters. So how much did we really stretch the spring? 5, right? So the spring is stretched by 0.15 meters minus 0.1 meters, which gives us 0.05 meters. So that's how much stretching we actually did, was 0.5 meters. And we're told then that a force of 3 newtons is required to do this. So in terms of our proportionality, so we need to, 1, find K. So to find the proportionality constant, we need an ordered pair. So when we input a distance of 0.05 meters, what did we get out as the corresponding force? 3 newtons. Because we had a force of 3 newtons, stretched it this far, while our stretching was given here. So we get 0.05 meters corresponds to a force of 3 newtons. So now we need to solve for k. So we put this into our equation. F is equal to k times x gives us 3 newtons. And to be very, very explicit, what was a newton again? A newton is a kilogram meter per second squared. Is equal to k times x, which is 0.05 meters. So we divide both sides of our equation by 0.05 meters, and we divide by 0.05 meters. So our meters reduce out, those reduce out, and we get that k is equal to, well, 3 divided by 0.05 gives us 60, and our units that are left are kilograms per second squared. And that is our proportionality constant, k. So now we have our equation. F is equal to 60, and I'm going to suppress the units now. So our force is equal to 60 times x. Yeah, let's go ahead and calculate our work. So our work is going to be the integral from a to b of our force function times the distance that it has to travel. So now we need to calculate our upper limits and lower limits of integration. So coming back to what we did up here, we'll notice we stretched from 20 centimeters to 40 centimeters, but what was the natural length of our spring again? 10. So our lower limit is going to be 0.2 meters minus 0.1 meters gives us 0.1 meters, and our upper limit is going to be 0.4 meters minus 0.1 meters gives us 0.3 meters. So once again, suppressing all of our units, we have 0.1, our work is the integral from 0.1 to 0.3 of our force function, which is 60x times dx. So now we integrate. The antiderivative of 60x is going to be 30x squared, and then we evaluate that from 0.1 to 0.3. So we have 30 times 0.3 squared minus 30 times 0.1 squared, giving us 2.4. And the question is 2.4 what? Well, we know we're solving for work, so what should the answer be? Joules. But let's go ahead and verify that. So the units of our force function, k, were 60 kilograms over second squared. So this had units kilograms over second squared. And what were our units of x? Well, that's right here. They were in meters, right? And when we found the antiderivative, we squared x, so that would be meters squared. So a kilogram meter squared per second squared is indeed a joule, which is what we want. So our dimensional analysis does match what we were supposed to get, because our x went from 0.1 meters to 0.3 meters, which would give us square meters for our units. So it's interesting because we can use the dimensional analysis to make sure that our answer is correct and makes sense. Because if your units aren't right, you know you did some math wrong somewhere, right? It gives you a check to make sure that the universe is consistent, which it always is. So if your units don't match, it's probably something I did. You know, so, all right, let's take a look at our next one. So this one is a you try, but it's not quick, so we'll put you in groups to get started. All right, so let's talk about how we're going to resolve this. So we notice that the big difference is that we were given work instead of a force this time. So our work is 4 joules, and we're told that the spring is stretched from its natural length of 28 centimeters to a length of 40. So then our lower limit is going to be the following, is 20.28 meters minus its natural length, which is 0.28 meters, equals 0. And our upper limit is going to be 0.4 meters, take away the natural length, which is 0.28 meters, gives us 0.12 meters. So we then can use that to help us solve for our constant k. So we get the equation 4 is equal to the integral from 0.12, or from 0 to 0.12, kx dx. The k is a constant, so we can just pull it out of our integral altogether. And that leaves us with 4 is equal to k times the integral from 0 to 0.12 of x dx. Well, the antiderivative of x is x squared over 2, so we get k times x squared over 2 evaluated from 0 to 0.12. So that gives us 4 is equal to k times 0.12 quantity squared over 2. So then, simplifying that up a bit, we have 0.12 squared, and then we divide it by 2, which gives us 0.0072. So we have 4 equals 0.0072k, and we divide by 0.0072, and we divide by 0.0072. So 4 divided by our answer from the previous line gives us this. Pressing math, we can turn it into a fraction, and we get 5,000 over 9. So if we're ever given a decimal, we should always try to turn it into a fraction so we don't introduce rounding error. Because if we round off too soon, it's going to cause problems. And if we can't convert it into a fraction for exact computations, it's probably best to store that in our calculator for later use. So to remind you, if you want to save a value in your calculator, you go down the left-hand side, you press the STO button for store, and then you just choose a letter. So since this is our k value, I'll just go ahead and store it as k. In this case, since we have a nice fraction, the storing is unnecessary, but sometimes it is necessary to do this to keep from getting too much rounding error as we're working through a problem. So we then saved that k for later. So we have k is equal to 5,000 over 9 after converting to a fraction. So now, after doing all that, I almost forgot, we're not done. What is it we're supposed to find? How much work is needed to stretch the spring from 30 to 38 centimeters? So we need to find our new upper and lower limit. So we want to go from 30 to 38. So we're going to have 0.38. And then what was our natural length? It was 28, so 0.28. So that gives us 0.1. Our new lower limit is we're going from 30. So that's going to be 0.3 minus 0.28 gives us 0.02. So now our work to do this is going to be the integral from 0.02 to 0.1 of kx, well we just found k, so 5,000 over 9 times x dx. So we do our derivative, our antiderivative, so 5,000 over 9, and the antiderivative of x is x squared over 2. And we evaluate that from 0.02 to 0.1. So we're going to get the 5,000 over 9 times 0.1 squared over 2 minus 0.02 squared over 2. Well, let's put all that into our calculator. So we have our 5,000 over 9, or since I have it saved in my calculator, I can just go alpha k. And notice if I do that, my calculator now firmly believes that k is the fraction 5,000 over 9. So I have k times 0.1 squared over 2 minus 0.02 squared over 2. Hit enter, I get this. Once again, math fraction. And we end up with a nice number right there. So after all that, our calculator tells us that we have 8/3 or 2 2/3 joules of work would have been done. All right, so our next example is a 200-pound cable is 100 feet long and hangs from a building. How much work is required to lift the cable to the top of the building? So if you think about this, what it's telling us is that we have 200 pounds of cable and it's 100 feet long. So when it's, before I pulled up any, how much weight is hanging over the edge of the building? All 200 pounds. But say now I pulled up 10 feet of this cable, or let's say 50 feet, which is half of the cable. So half the cable sitting on the top of the roof now. Am I picking that up anymore? No. I'm actually only going to be pulling up 100 pounds of cable after 50 feet because that 50 feet that's hanging down is the other half. So every time I pull up some of this cable, I'm actually pulling up less and less weight, right? So that's really the idea. So if work is equal to force times distance, my force is changing every time I move that cable up, because more and more of the cable is now sitting on the roof or is inside your winch or whatever it is you're doing to move this cable up. So let's see if we can figure out how this is going to work. So I'm going to start by drawing a picture to help me visualize what's going on. And don't laugh, because I'm a terrible artist. I do stick people. So we have our stick person on top of our building. And we've got a rope hanging down off the building down here. And something you're going to find in engineering and physics is oftentimes we change our coordinate system around to make the math easier. So I'm going to define where my person is standing as the point 0, 0, and my positive direction is going to be down. If that's the case, when I'm down here at 100 feet, I'm going to have 200 pounds of cable, right? Now, if I'm at the top at 0, 0, if I have no feet of cable, how many pounds do I have? None, right? Because it's 0. Because that means the whole cable is sitting up on the roof. So now, let's visualize a little piece of this that is delta x thick. So each little delta x thick piece, well, how far am I going to have to move it? Well, wherever it is located, the distance from the roof to that delta x piece is going to be x, right? Because that's the way I defined my coordinate system. So I'm going to be moving each piece of rope x units, right? So the one at the very, very bottom is going to go 100 feet. The one that's only 1 foot from the top is going to go, what its x value is 1 foot, and then it's on the roof, right? So the distance to every delta x chunk is x. All right, so now we need to find something to do with this. So the first thing we have here is we need to find our density in this case, or our linear density. So what do we know? I have 200 pounds of cable, and it's 100 feet long. So if I take 200 pounds of cable and I divide it by 100 feet, 200 divided by 100 is 2, and that tells me that the weight of that cable is 2 pounds per foot. So that's referred to as its density, or in this case, its linear density. So my unit rate of change is, for every foot I pull up, how much less weight am I going to have? 2. So one way is to think of it that way. I also made a coordinate system, right? With 0, 0 and 100, 200. I could just calculate the slope, right? So my y2 is 200 minus my y1 is 0, all over 100 minus 0, which gives me 200 over 100, which is 2 over 1, which is 2. And what was it that the y's measured again? Oh, the y's were pounds, and the x's were feet. So whether I think of it algebraically or in terms of a proportion, I get the same density. In either case, it confirms that our density is a unit rate of change, right? Something changing per something. It's a slope. So we have our density then is 2 pounds per foot. So now we need to find the change in work. So our change in work, our dW, so work is force times distance. So our force is going to be our density, which is 2, times our delta x, so dx in this case, times how far am I lifting each chunk? So each chunk is going x units. So that's going to be my distance. So then we get that our change in work for every x is 2x dx. So then to add up all of those little tiny slices of work, where are we going to integrate from? From 0, and how long is the rope? 100, right? So we're going to integrate from 0 to 100 2x dx. Well, 2x has a great antiderivative, which is just x squared, evaluated from 0 to 100. So that gives us 100 squared minus 0 squared, which gives us 4 zeros afterwards. So that would be 10,000 foot-pounds of work to lift that rope all the way to the top. So notice, since we were given not a mass, but a force, it made it a little bit easier. If we were given masses, we would have to work a little bit harder and multiply by little g like we did back in the first example. So in the homeworks, you're going to have both types of problems. Some in Imperial, some in the MKS. So make sure you're paying attention, because the constants you have to multiply by will be different depending on what you're doing, but the basic setup is almost always the same. All right, so we're going to jump over you try 3 for a second, and we'll come back to it, but I want to make sure we can do example 4 if we have time, because example 4 is a great example. So a tank has the shape of an inverted circular cone with a height of 10 meters and a radius of 4 meters. It is filled with water to a height of 8 meters. Find the work required to empty the tank by pumping the water to the top of the tank. The density of water is 1,000 kilograms per cubic meter. Okay. So let's draw a picture of this situation. So we have a tank that is an inverted circular cone. So it looks like an ice cream cone, like one of the cone ones, like this. And we're told a couple of things. So its radius is 4 meters, and we're told that its height is 10 meters. We're then further told it is filled with water to a height of 8 meters. So we've got our cone here, and it's not filled all the way up. And our goal is then to pump all of this water out of the cone by bringing it to the top to get it out. So how are we going to do this? Well, let's imagine what each little cross section of water looks like that we're going to have to take out. So imagine I have a little disk of water here, right? But the problem with this is, as I go down further and further in the cone, the radius of those disks are going to be changing. At the very top, the radius is 4. Down here, the radius is much less than 4. And in fact, at every height, the radius is going to be different. So in order for us to find what we're looking for, we need to figure out a formula that relates the radius to something else. So there are several ways to do this. So one such way is to imagine a two-dimensional projection of a cone. So if you were to cut it in half, it would make a triangle that looked something like this. And now imagine a line dividing that cone in half. Well, if we did that, then we would know that this is the radius of that cone, right? If we took a cross-section right through the center. So this would be 4, and we would also know then that the entire height of this triangle would be 10. But what we are interested in is, well, what is the radius at any given height? So we have some choices, and there are multiple ways to do this problem. The math will work out the same either way, but not all choices are as simple. So as mentioned in the previous problem, we have latitude on where we're going to put our origin. Since we're trying to pump the water out of the top of the cone, I'm going to define the top to be 0. So if I look at it this way, when I'm at the top of the cone, when I input 0, what's my output going to be? 4, right? And then if that's the case, then the bottom of the cone would be down here. The height is 10, so if I input 10, what would be my radius at the very tip of the cone? 0, right? So right now there are two different ways to do this. So if I imagine that I want to figure out what r is, if I have my origin here, the distance from the top to r is x, and then the distance the rest of the way down would be, well, if this distance is x and the whole thing is 10, what would this distance be? 10 minus x, right? So there are two different ways to get what we're going for. So now we actually have some similar triangles. This small triangle here is similar to the big triangle out here. So these two triangles would be similar. And the way similar triangles work is that the proportion of sides has to be equal. So if we set this proportion up as big over small, we would have this side is 4 divided by r is equal to our big side is 10, and the small side of our green let me color code those because I think it'll make more sense. Equals, so we have our 4 over the proportional side, which is our radius, which is r, all over our big side is going to be 10 over our small side is 10 minus x. And if we solve this equation for r by multiplying both sides by r and by 10 minus x, so instead of saying it that way, I'm just going to cross multiply because I don't have a ton of space. So we cross multiply, and we get 4 times 10 minus x is equal to 10 times r. So then we have distributing 40 minus 4x equals 10r. And then we divide by 10, and we get r is equal to, well, negative 4 divided by 10 is negative 2/5 or negative 0.4. So negative 0.4x plus 4 would be our relationship for r. It says the radius of that cone is equal to negative 0.4x plus 4. So something I wanted to mention, I also coordinatized, right? I gave you those ordered pairs. Let's calculate our slope. So if I did that, my m would be y2 minus y1, so 0 minus 4 all over 10 minus 0 gives me negative 4/10, which is negative 0.4. Then I would also have this point right here, 0, 4. Oh, that would tell me my equation is negative 0.4x plus my y-intercept, which is 4. Oh, they're the same equation, right? So geometry can often be used, but a good coordinate system will also help you derive the same things algebraically. So in almost all of these problems, there's going to be a geometric way to think about it, and there's going to be an algebraic way to think about it. For some of us, the algebra way is going to be so much easier than trying to remember the geometric way. For some of us, the geometric way is going to be a lot easier. Remember, I'm goal-oriented, not path-oriented. So if one of these two methods makes more sense to you, that is the right method for you to use to do that problem. It's always good to have choices, so if you can master both, that's even better. But we have choices. So now we need to figure out how much work we need to do. So we finally know what our radius is of this little piece right here, right? So we need to figure out some things. So the volume of this little disk then that we've drawn, we need to figure that out. So what is its volume? Well, we know that it's going to be delta x thick, and then what's the area formula for a circle? Pi times our radius squared, and we just found out what our radius was, which is negative 0.4x plus 4 squared. So that's the area of the base times its height is delta x. Times our height. Well, that gives us our little volume of this green cone, right? Well, we have a volume, but we need to figure out what our mass is. So if you know a volume, how do you find mass? Well, mass is equal to density times volume. So that's something we might need to know. Mass equals density times volume. So we have a volume, so our change in mass, dm, is going to be our density of water, which is 1,000 times our volume, which is what we have right here. So 1,000 times pi times negative 0.4x plus 4 squared. And I'm going to replace my delta x with a dx because we're going to be doing an integral in a bit. So now we have our mass, or our change in mass, but to find work, we don't need mass. What do we need? Well, we need force first, right? So force is equal to what? Mass times acceleration. So our dF is going to be our force, is going to be mass times acceleration. So we have our mass, which is what we just calculated. So 1,000 pi times negative 0.4x plus 4 squared times our acceleration. And what's our acceleration due to gravity? That was our 9.8 meters per second squared, dx. So now finally we're at force. So to find our work, what do? We integrate. So our work is going to be the integral from a to b of df, all of the change in our forces. So in our case, what are our limits of integration? Well, where did we start? At 0. And we have to go to 10. Or do I? We got to be a little careful. This is where it gets tricky. How full was the tank? So this was all the way up at 8 meters. So then if it's at 8 meters, our x is the distance from the top. So what would this distance be? Yeah, it's going to be 10 minus 8, which gives us 2. And then where are we going to integrate from? Well, not 0 to 2. That would lift only the water out of the first 2 feet of the tank. Our water is all below that. Our water goes from 2 all the way down to the bottom at 10. right? So our limits of integration are going to be from 2 to 10 of this integral. I'm going to do 9.8 times 1,000, because that just moves the decimal over 3 places. So 9800 pi times negative 0.4x plus 4 dx. So then from here, we pull our constant out, 9800 pi times the integral from 2 to 10 of negative 0.4x plus 4, I dropped my square there, squared dx. So from here, we just do the integral, which I'm not going to write out because we're out of time, and the final answer turns out to be 1568 pi times 2048 over 3. And then you can multiply that out. But we'll stop there, because once we have the integral, I know you guys can integrate a polynomial. It's not too hard. All right.